a pleasure to introduce Leonardo Cavenaghi. So he will talk about the F-bonds.
Yeah, so I'd like to thank you very much the opportunity for being here, especially because this shall be some kind of a small digression regarding the topic of the conference, but not only, I mean, it has like a different character in the sense that there will be three lectures. This is the first one, and it's entitled Actuando. And the purpose of these three lectures is try to give insights and maybe some like technicalities on this new theory of atoms. So earlier in this year, there was a paper that's not this, but essentially this resumes well the theory, so theory of atoms. Go to answer code. Maybe when you come to you that we will talk the crowd hearing. And so the idea for today and tomorrow is especially try to deal on this theory, at least the way that I like to think about it, because after this, and this is shall be intended, like I intended that this will be the content of the third lecture. We're gonna explain how this theory works on the G equivalent section, so G equivalent atom theory, and maybe some words of this on the output setting, and this is based going to work by Gatzerkov and Kotsevich. But the first disclaimer that I would like to bring here is that I'm no financial geometer, and I more or less ended up doing this kind of stuff because I was looking to some hypersurface singularity sleep, and more or less in the spirit of Alim stock trying to understand whether it could like retain the smooth formation on the link, or the heads of the spheres and this kind of stuff via some kind of algebraic geometry. And to begin with, we'll deal with this F bundles story. But in practice, and that's something that I would like to make very clear through this series of lectures, is that you don't need much to go to all this machinery to do computations and obtain your results. So some advertising, we joined with Professor Coven Concept, we are writing some lectures to know how to do this, to teach people how to do this in practice without caring much about the technicalities. We intend to finish this soon. The first paper of theirs took 15 years, so maybe in like half of this it will be alright. But anyway, so we have to understand first what are F bundles. So first question is what are F bundles? And maybe the second important question is why do we care? And the answer about why do we care is actually where the computation of CERN lies for this theory. So I thought very much about how to start this talk, and then I'll start in a way that I didn't. See? So let's do the following. We will start defining what are bundles. So we shall fix K to be some non-Archimedean field. Char K to 0. Then I pick D is formal spectrum. Okay, you. So if you like, you can think of D as germ of K analytic disk. Yes.
characteristic of residue field is also zero.
Yes, yes,
So it's non-linear.
yes, yes, yes. For instance, to us, the most important example of K shall be this field of Poisson series. So there's no penalty disk in the parameter U. Okay. And then the definition of an bundle that will herein denote like H. So this is an H, Helge H, connection, and then some B. This shall be the following data. So we pick B. This is smooth. K analytic super variety. And then H is K analytic super vector bundle. Over attentional B cross D. And the third guy that we shall consider is NABLA, a Nero connection with most. That's right. At most, at U equals to 0, and such that it is a flat connection. Then 2. And 2 and 3, that's something that's very helpful, and actually is where the core of many computations reside. I mean, of course, it is very much needed also. So when you look to this following covariance derivative here, so you have your parameter U, then you pick U squared and take the derivative. So you look to this covariance derivative, then you ask that this guy here is regular. Okay, so the possible singularities disappear along this direction. And also, for any local vector field C on B, so let's adopt the notation maybe then. This operator also is regular. Okay. One of the main importances of this kind of data that you have in this picture lies on its residual aspect, meaning what shall happen when I restrict to U equal to 0.
B is not smooth.
No, B is, yes, is smooth K and supervariant. The possible similarities comes from the fact that you have this U there. Okay. So one nice stuff that comes from these bundles are its residual data. So at finals, they use some residual structure. What shall be this? Well, let's denote by age and then 0. This shall be vector bundle, vector bundle over B. That's given just by, well, you said this guy. So the fibers, let's just factors. So fibers, these are just fibers. Okay. And then there is also a Higgs field. Meaning, if you look to me to be this guy from H0 to H0, that's precisely point. So you pick some local vector field, and then you map it to the residual part of this guy. And it satisfies the following equation. So the H0. Okay. And the other residual data that you have is this guy here that you're gonna call kappa. So kappa. So let's put this as the first basically information. Then you put this section, second residual information, and then you look at the third residual information. That shall be the operator kappa here. That is, we have used one of the regularity conditions, but we have asked for like a second one, and then it shall be simply this guy here. Okay, so what is the picture? Maybe better before saying the picture, let's put another definition. What is maximal? Yeah, I'm always thinking about super geometry. So like locally, I just take instead of the ring of functions, like it's just the super functions. So we have grading on the variables. So think about the following, and that we're going to do this example explicitly. What is the main source of stuff that you like? Pick a homology, right? So it has even and odd parts. So it has a Z2 grade that you can consider. And so you take multiplications according to this kind of grade. So this is how that I mean. You have even and odd variables because you have some kind of Z2 grading on your space. And the even variables they commute, the odd variables they don't commute. So you can think of the odd variables as one forms and the even variables as polynomials. Just this thing, but we shall see this more clearly in this homology example. But it's super geometry. That's all I'm thinking. It's taking coordinates with parity. That's all.
So is H0 just for the even part, so to speak, of it, that H? Or is-
H0.
Yeah, H0, is it, you start with an H, a super vector bundle? thing.
Yeah. I
That
started with a super
Or is
vector.
the sub bundle of that?
No. Let's
Or
see.
is it a different thing?
No, it's a
of-
different thing. Yeah.
different
no,
thing.
yeah.
is also super.
Sorry?
H0 is also.
Yes, alpha super. Yes. Let's see this
Oh, I
more
see.
precisely.
So far, there's a super structure did not think that I'm.
No, in no way so far. No. I mean, sorry. There is a reason, and this is the main example. That's called a model maximal bundle, whatever it is, but we're going to define this. So Gromov written data has problems about convergence. This theory is built upon Gromov written data. When you do also this kind of connections with possible poles, you have problems like depending on the way that you approach the zero. So if you're like consider you some thermal discovered complex numbers, depending on the directions on the complex planes that you choose to approach zero, you can get different behaviors for the solutions for complex sections. So the non-Archimedean setting is built to circumvent this kind of issues and make a good use of Gromov-Witten theory. Essentially.
But everything you said so far works over
Yeah,
single problem.
yeah. So far, I mean, there is no need to use the analytic story. This comes from the fact that we are going to apply this theory on a very complete model built out of Gromov-Witten data. And also, so far, there is no usage of Z2 grading story at all.
So sometimes you're trying to avoid the question about conversion.
And
Stokes
Stokes phenomena.
Stokes.
Yeah, exactly. most importantly, yeah. Yes, perfect.
It's probably also no coincidence that it somehow resembles the pattern of Platonic standard paper of
Not at all. I mean, actually, one of the main examples, if you like this definition, is some kind of a non-analytic, non-Archimedean version of variations of non-multiple structures. You can think like that. These are examples. So not at all. I mean, it's not surprised at all. Okay, so then the definition of maximal bundle is the following. So we pick a point here on the base, and then we shall say that this F bundle is maximal at B if, so you look to this evaluation now. Oh. It look better with this. With the middle. That's all. So we have this map C that goes to C, right? Now I can define, so this is the map for me. I can define the evaluation map for some vector. Me, this is just B, C, and it's to make C. H, or H belongs to H is 0. So in a sense, what I'm saying to you is that the evaluation map, when we compose this, then you have a map from TV to H is 0. So just some definition. So I'm just made some notation. This F bundle shall be maximal at B if there exists some H belonging here, such that this map here, when we evaluate at H, is an isomorphism. So, said in other words, B, so the tangent space at B of the base can actually be made isomorphic to this residual part. That is this H 0. So you can recognize the fibers of your base B whenever you set the U parameter equal to 0. Why this is nice? Because then we can use the endomorphism structures of this bundle H to give a algebra structure to the tangent space by pulling back the product, the composition of the operators. So, because, and then of course, dot bundle moreover, it shall be said maximum if it is maximal for all E in D. And the proposition, so that we can finally draw a picture, is the following. This fact that you have a maximal F bundle, if you pick maximal F bundle, then for every P, this tangent bundle carries the structure of unital. Actually, shall be even graded because we have super stuff associative, commutative, algebra. So it means that the following picture is true. So you have your super manifold B here, so super variety. That so far we have used nothing about being super. Okay. Then which point that you click here, you look the fiber at this point. This fiber here comes with the structure of a product. That's the note made. That's the note convenient here already. Star. That shall be this product here. That depends on this point. Okay.
You stated the product comes from H.
Yes.
Let me see where the product on H was.
Because so you look to endomorphisms of this because these are connections, right? So you have when you pick a vector, then you have an endomorphism of your bundle because this is the residual operator given by covariant derivative. So which guy that you pick, you get an endomorphism of your bundle. So the point is what's going on here, and this is being identified with the image of the.
Think of this n space to be infinite dimension.
You find the I mean,
It's finite.
yes, it's finite. For example, with the 3, it shall be the common.
So you have this algebra and this finite infinite.
Yeah.
Is it quiver algebra? Yeah.
I mean, a priori can be anything, but in the example that we are shall be most interested, this guy shall be precisely the following. We shall look, we'll enter with some homology over C, then we look to expect homology.
That's like homology.
Yeah.
Yeah.
And then you pass to the non-Archimedean setting, and then this shall be the quantum product. Mhm. But let's not get like a spoiler now for a moment. So the nice thing about this picture is that you have your base, then you have a product structure that's given by the image of this new guy. And not only, I mean, there's because now you have identification between this guy and the base, you actually have a vector field. So definition of what goes by the name of Euler vector field.
This is really the Frobenius manifold form. What's the difference?
I mean, it's actually the Frobenius manifold, the residual part is the Frobenius manifold in the non-Archimedean setting. But the main difference is that the Frobenius manifolds, they come with flat metrics, and we shall need to make some identifications later. That does not, so this metric does not go well. So that's why we need to talk about that part.
Where's this thing non-Archimedean?
So far nowhere.
Okay.
So far nowhere. Yeah. So this, but yes, I mean, Helge's point is the most precise one. The residual part is something that's just Frobenius man. That's all, nothing but that. But extended to the non-Archimedean side to avoid convergence issues and this kind of stuff.
That comes in the next one.
Actually, we're gonna do maybe today. Let's see where we go because
More or less.
the like. Yeah, maybe today. Let's see. So the order vector field then, we have two residual guys, this kappa and this mi. The order vector field shall be the vector field that relates them both. So is the unique. And now to partially answer one of the questions, where is the Z2 grading coming? I mean, are you using super something? Then the unique even vector field you such that when you apply it to mu, this is kappa. So then what we have is in this point, so we have our V, and then there is some vector field here. So that on this point gives you this UV. And such that you can actually identify out of this data, we can actually see kappa as, because we chose to denote the product here by star, then you can actually write this as some kind of notation like this. EU star. That's what this equation of one. So then you have this kappa, and the picture is like that. You have some V that to those that like, you can really think this as Frobenius manifold. Then you have a product to each point, and then there is distinguished vector field such that it relates with one of the residual quantities. That is internal multiplication. So you have this guy. Okay, and now one thing that shall partially answer Helge's question is the following. So if you look here, what we actually have is a rule that tweaks B, okay, assign this operator. So this is a vector, tangent vector to the point B, and you have the multiplication at the point B. So it gives a free entry, right? So it's actually like some TB. So this guy, kappa B, is an endomorphism. And whenever you have some kind of endomorphism, you want to compute eigenvalue. Let's see. So first claim is the following. Now maybe put a theorem. So theorem mean almost out of nothing, just some definitions and some properties. Then there's a theorem already. This is, there are two versions of this, one in the formal setting, one in the non-Archimedean setting. So it's both either as I call concept from the view, but also could be, then Tony U, Jane, Jane. That is the following. So we have a maximal F bundle. Then you pick a point B belonging B, and you look to the decomposition of H B0. That's right. Lambda B0 in terms of terms of the eigenvalues of this kappa B. Okay, that's the hypothesis. So you pick a point and then you look to, in terms of, generalized eigenspaces. In terms of the generalized eigenspaces for the eigenvalues. Kappa B. Now it comes the non-Archimedean story. So this is the hypothesis. What is the thesis? Then there shall exist some U where they belongs to, such that when we restrict your F bundle to this neighborhood of B, then this guy here decomposes. I'm just writing a external sums. I'll tell you in a moment what is this. External sums of certain A model of certain F bundles, maximal F bundles over some base to each number. So you yeah, great, yes. Yeah. So locally your F bundle splits in external sums of other F bundles. What are these external sums? What? You pick as fiber just for two F bundles, you pick as fibers the summation, and then the connections are also there. It's like just the sums. It's like fibers. But the base is products. You have this decomposition. So this is where like a non-Archimedean setting plays a major role. Because we start with something that's pointwise, and then you build analytically some like a F bundle close to this. So it means that from point data you can really build some story. This is like a how does the proof close? You have to solve recursively some PDEs that will define this kind of quantities. And this is one of the first two. This is very important. So atom theory, whatever this is, relies firstly on this result, and second on a result, analogous result to blow-ups. Whenever you have blow-ups, you would like to make some kind of construction work there. This is definitely going to do on the second lecture, and also maybe give the example of the cube. So this is how this goes. I mean, if you see just playing around with the definition of and the construction, the setup, you can prove a result like that. So our main interest is the following. The point is that you can build some base, right? I mean, a priori there is no one. Yeah, I'm just saying that locally, when you restrict your bundle, you build this F bundle in another place, and then you have isomorphism of F bundles. There is no a priori, no relation between.
Is U an open set and B?
Yes, yes. At least
So you're saying it splits on an open set?
yes, yes, yes. So I'm saying that this F bundle it splits on the set. I mean, if what is hidden here in many ways is that when you have like this quantum homology story, you want to do analytical equation and relate to different quantum homologies. With this technology, you avoid all of this. That's what is saying. Yeah, so this the summation here is just like that. So let's class. This is external sum.
Isn't it just the property that Jordan blocks are an open property?
I mean, yes, yeah, but yeah. No, but anyway, how you build it? Like, you have to make this. But yes, I mean, that's very important. So the external sum is the bond. So whenever I have two F bundles, say 1, 1, 1, then the external sum of these two guys is just the following F bundle here. So the base of this shall be V1 plus V2. And then here we just pick, I will just explain in a moment what this is. A1, then 2, 3, H2, and then search information here. Tilde, where E13 is the following. So we have A1. Make sure I'm not doing rubbish. So E13 is just, so you have B1, then B2, then the disk, you just project to B1 plus D, and then B23, you just project to B2. I mean, is what we expected to have in terms of behaviors. No, no, I mean, actually, it's really about so you compute the eigenvalues of this operator in the point B. You may have like some quantity, and then these are the generalized eigenspaces, like the composition in terms of the generalized eigenspaces out of this, and these are the same data object. I mean, this is half bundle. It doesn't see much, but this is one good point. Now, what is this A model F bundle that we want to discuss? So,
For example, the same number of item values as the dimension of B.
no.
Yes.
Counter multiplicity is the same as the tiny space of B. Yes. So yes. You're yes. Counter multiplicity, yes. Yes, exactly. Okay. So then main example.
You view this something about the view. Algebraic is also.
We shall do algebraically post. So let's always keep in mind, yeah. For doing this kind of decomposition, we suppose algebraic. So I mean, herein and to the other talks, you can always think of this line. This is. Yes, this is the point. This part, yes. So the main example is this A model at bundle.
See, that's why I'm not communicating. I asked you where it is, and then it's right here. That's what you. Not communicating, so.
Yeah, I mean, where? See,
Yeah, you have a non-communicating evaluation.
Yes, here.
Yeah.
I mean, to the complete examples, like here. To the definitions that we're doing, like there was no need
Yeah,
to,
I could-
so now, but now it becomes like a special. Because, so whenever you have some kind of a smooth projective variety, then you can look to its homology. So let's look to, say, its red homology. And it has a pairing. But if you use Norwegian data, a nice way to think about this is some kind of deformations of the standard cup product that we have here. So we have a cup product. So let me just say Norwegian data meaning numerative geometry. Then you can actually use the meaning of quantum homology. Of X. And quantum homology. So quantum homology, you can really think as some kind of. So you have your homology being, vertical homology, and then you have now a family of products. Family of products. Let's say cut-like products, but I mean just to emphasize some kind of deformation. And whenever you want to specify some product, you do this choosing basis. Then you look at A star B X as E2 graded. Now, this means that we are considering like even and odd classes in homology, right? So pick graded basis. Alpha. That's the null time. The dual basis. I always consider if grading. Okay. And then these products, they can be simply written like that. Roughly, I'm masking labs when comparing this kind of stuff, but by actually just assigning some new structure constants, right? Yeah. Now the secret is that this is structure constant. They are not constants, they depend. So not constant. They depend on choice of some points B in your formula. For some choice of B, you have different structure functions. This is how it's specified. And we call this guy here lower region coefficient. Actually, the third derivatives. That's us.
Yeah, Mr. Who is B here? Who is B?
You always have
B here.
around the space.
Yeah. I mean,
B,
this B here now just means something else. It's bad homology. Let's just not use it. Just bad homology.
But who is B?
B
Space B?
is for bet.
No, I understand that now, but your space B.
I didn't write it yet.
it's just around the space.
Yeah, I just didn't write it yet. because I was saying that you have this potential. Yeah.
Yeah, but what is it here?
Well, I'll tell you now. So we have this discussion over Q. Now you pass to the non-Archimedean setting. Then you extend your thermal breathing potential. Then you just pick a ball on this homology with non-Archimedean. That's all.
What do you mean you extend? What does that mean?
I mean, you have to look to this loop covering, like take into account the fact that you are in the non-Archimedean setting, and
No, I mean, what you want to do is you go to the value range of the thing,
yeah,
and then you have to show that you're splitting it to through the value.
true. And this is the encephalography again. Yes. Yes, you have to do.
You give it proof.
No, I mean, not myself.
No, but the numbers at least, right? That it would be the classical ones, right? I mean, the structure,
I mean, when
when you say extend, that's why I'm asking.
I mean, one of the main reasons that you choose going to this guy here is that after you do this, all these number general constructions to put your hands on the facts, you can really like forget somehow and then just look to Q bar. So all the impedance will be like for homologies equations in Q bar. Now, whether you can go back to Q, there is expectation, but it's not done. I mean, but this is maybe not to what. You know, well, then just to conclude, one more minute, and then we describe better the model next time. But whenever you have your homology, then you have the potential, and then you want to do a model of bundle of this data. So this is just like the preliminary story. So what is the model of bundle?
But except if the potential in this formula, let's see.
Yeah,
You have the third derivatives.
third derivatives of, I mean, you have Gromov-Hodge potential, right? So it depends on the coordinates.
I can remember this in this formula.
No, I don't
They're
write.
not written.
Yeah,
they are.
it's a generating function, and then you take the Taylor series and the potential. Usually.
Yeah.
Very standard.
No, it's not written.
Yeah. I mean, I just said it's third derivative thing. Actually, what the point is that C alpha beta gamma, this shall be the third derivative, P alpha, P beta, P gamma, for certain potential. Yeah. That's it. Okay, so then we have to specify the model. What you do is you shall pick age to be what? Let's denote this homology here by age. So age, then it tensorize Q. Now we choose explicitly A to be resolved. Series. Then K. And then this shall be the trivial. Let's put age is the trivial vector bundle over some B G with fiber H Q, where P is some ball in H. So connection. So the connection is given as follows. The derivative, the direction U, this is D du plus U minus 2K plus U minus GR. I'll tell in a moment what are these guys. PT alpha. This is P E alpha plus A alpha. Where A alpha then star, that's product purchase defined. A alpha is double star. This product. And then GR stands for grading. So if D is D-dimensional, then this goes to D, I minus D over 2 identity AIX. And finally, A is minus 1 EX plus alpha degree alpha degree D alpha minus 2 D alpha. D alpha. This is roughly the scheme of the starting with setting. And so what is the idea for tomorrow? Then, once this is built out of the new projected variety, we want to understand whenever you do blow up, how differently models behave. So blow up for a model. Once this is done, we can understand how out of this data you can try to build some kind of variation variance. And if not tomorrow, on the next lecture, sketch the argument about it. Thank you very much.